Greetings. Welcome to our 17th episode of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign.
And hello, everyone. My name is Jen Miller, and I'm the coordinator of the Fabricated Geomembrane Institute, or the FGI.
On today's episode, we are going to focus on the Yeager Airport reinforced soil slope failure case history. Our guests today are Ryan Berg and Jim Collin. Ryan is president of Ryan R. Berg and Associates, and Jim Collin is the founder of the Collin Group Limited, and both gave an excellent webinar on the Yeager Airport reinforced soil slope failure. Ryan and Jim, thanks for squeezing this podcast into your busy schedules and helping us answer some of the questions that we received about the slope failure after the webinar. So let me start right in with question number one. The question is, I believe it was stated that there was no geotechnical instrumentation monitoring of the RSS before failures. What recommendation would you have made for monitoring of the RSS, and is the new retaining structure at the end of the reconstructed runway instrumented? So Ryan, if you can jump in there.
Okay, so that's a two-part question. On the first part, the original RSS structure was not instrumented. And when we think about scaling up structures by an order of magnitude, there are certainly questions that come into mind. One would be, what is the maximum amount of strain we would see in the geogrid in the as-built structure? So one item of interest would be to answer that question and to instrument the geogrid as the structure is being constructed. Certainly there are other questions that could be developed and corresponding instrumentation for that original structure. The second part of the question was about the replacement structure, and yes, that is heavily instrumented. That's a tie-back structure. The anchors and tie rods are instrumented. There's shape arrays within the structure, and there's a PS INSAR monitoring system for the structure itself and the surrounding area.
Great, Ryan, thanks. Question number two. The fully softened model usually corresponds to a contractive soil. Does this analysis did it take into consideration that at the start of the design? And Jim, I think you're going to handle this one.
Yep, thanks, Tim. Not that we found in the design document files. The original design stability analysis used 40-degree friction angle for the strength of the foundation soil.
Okay, thanks, Jim. Would you recommend the use of drains to control the seepage and the groundwater level since the interface was sensible to this parameter?
Yes, we certainly would always recommend the use of drains behind and beneath reinforced soil slope structures, and only eliminate them if they can be engineered out. But generally, they're always recommended.
Yep. Okay, Jim, was colluvium or soft soils left in place at or below the toe of the RSS structure?
Yes, there was a shale, claystone, and a coal seam zone below the base of the RSS. Above that material, we're not sure what was there because during the failure, that material was taken. But there definitely was a clay shalestone layer there at the base of the RSS.
Right. And I think you mentioned in the webinar that was sort of the difference between the unreinforced side and the reinforced side, that there was a rock or a hard ledge under the unreinforced side.
Correct.
Yeah. Okay, Ryan, for the shale claystone interface, it appears that it may have taken 8 years or so to reach the fully softened strength condition from its initial peak strength. Any comments about that?
Again, our work showed that we were approaching the fully softened shear strength when failure occurred. We don't believe we'd fully reached that strength level yet, but we're certainly approaching it when failure was triggered.
Yep. Jim, how did you model strain softening for the shale and geosynthetics in the analyses?
For the strength reduction method, for the shale interface, we used, maybe we can start that one over.
Well, just if you could briefly describe the strain softening modeling for both the shale interface and also the geogrids or geosynthetics.
Yeah. So in our deformation analysis, we reduced the strength of that interface in the modeling from a peak strength to close to the fully softened strength, and failure was initiated. With a limit equilibrium analysis, we used the fully softened strength. For the geogrids and the limit equilibrium analysis for the different stages, we used the long-term design strength, the exhumed strength with creep reduction for our different cases analyzed.
Yep.
Great, thank you. In your opinions, what are the measures the design engineer should have or could have taken during design and construction to avoid this RSS failure?
As we discussed in the webinar, the key actions that we believe should have been taken is first, a more thorough subsurface investigation should have been performed, including a detailed geologic investigation. There should have been more details provided both on the plans and specifications in regard to foundation preparation and benching of the backcut rock. Furthermore, we believe that chimney and blanket drains should have been detailed and installed in the structure. And finally, we believe an external peer review should have been used in this structure due to its magnitude and uniqueness.
Yep. Okay, Jim, were any of the analyses and methodologies that were available when the initial design, were any of the analyses and methodologies that you performed or you used, were they available for the initial when the initial design was conducted?
Yeah, I think you're talking about really the state of the practice or the state of the art at the time the original design in 2005 was performed. We didn't talk about in the presentation because of time constraints. We did a 3D limit equilibrium analysis that definitely really wasn't available at that time, and that was important in our understanding of the anisotropic effects of the reinforcement. However, the 2D limit equilibrium analysis was certainly available. There have been some changes in how easy it is to run that software, but that was certainly available. And while numerical modeling was available also at the time, it was not a standard design tool. However, we felt that for the structure of this magnitude, it was, in our opinion, warranted to do that numerical modeling.
Great. Okay, Ryan, the necessity of adequate drainage in RSS projects and the preponderance of RSS and MSE wall failures of being attributed to the lack of drainage has been recognized for many years. Is there any information concerning the engineer of record's design choice not to include the chimney and blanket drains that were just mentioned, and what may have motivated this design choice to leave the drainage out?
There really wasn't any documentation in the files we reviewed in regards to choosing to eliminate or not include chimney and blanket drains. Typically, though, on projects, we see that choice being made as a cost savings measure. On this particular project, the specifications would have allowed up to 50% fines in the reinforced fill, but the actual construction used a very granular fill, so they may have assumed that they're going to get drainage through that granular fill, but there was a wide variety of materials being processed and included, and really no control of the water without chimney and blanket drainage.
Yep. Okay, Jim, during the webinar, the term granular fill was used. However, the laboratory testing at the failure surface had values of liquid limit and plasticity index, obviously indicating a cohesive or fine-grained material. Was this due to the degradation of the granular fill due to groundwater seepage or a different soil type?
So the failure surface was below the reinforced soil mass. In the virgin soil, existing soils there, and that was where we had our cohesive soil, the liquid limit and the PI. The granular fill used to reinforce the slope in the reinforced mass was granular, so it was not a degradation of that led to the liquid limit and PI.
Got it. Okay, Ryan, can you describe the mechanism that resulted in the fully softening of the shale interface? It seems that given the high confining pressures, fully softening would not occur.
Well, the geometry again here is a one-to-one slope. So when you look at the confining pressures above that interface that failed as it approached fully softened state, the confining pressures were approximately 5,000 psf. So they're not a function of the entire height of the slope. They're a function of the height directly above that interface. We believe that mechanisms for triggering the failure here in the soft soil was really a combination of the high shear stresses of the entire system and the presence of water and probably fluctuating water along that interface, and that those two led to the decrease in shear strength along this clay shale interface.
Yeah, Ryan, that's a good point. Partially saturated materials can still absorb moisture. It may not be as much at a lower confining pressure, but they still will absorb moisture. And of course, the shear stresses that you mentioned, of course, allow additional infiltration because the material can shear and undergo more deformation and let additional moisture in. So a progressive softening. Okay, so Jim, could you explain the strength loss due to creep in the analysis? It is my understanding that creep strain does not reduce strength until just before ultimate rupture occurs.
And that's exactly what happened. In this case, right, we had the reinforced slope. It started to move. We have settlement, or we had that tension crack at the surface of a couple feet, which transferred all that movement in the fully softened layer, transferred load to the reinforcement until the reinforcement load exceeded its creep limited strength, and rupture of the reinforcement occurred.
Okay. Ryan, in shale formations, would you suggest that it is necessary to bench the shale before installing the reinforcement, or is this dependent on the total height of the reinforced slope?
I guess I'd look at this question as, should you bench the back cuts of reinforced soil slopes? And the answer to that would be yes, both for rock and soil back cuts, and regardless of the slope height. However, that benching can become more critical for taller structures and also as a function of the geology of the back cut material.
Yeah. And if nothing else, you break up a continuous failure surface with a bench, so that seems like a good benefit as well. Okay, last one. Jim, great presentation. When I saw the original section with shortened geogrids at the base of the RSS structure and the lack of adequate benching to key the fill into the bedrock, I concluded immediately that the structure was doomed. Omitting adequate subsurface drains and maintenance benches is well below the standard of care for anyone designing a large slope. This was preventable. What suggestions do you have for the airport and other agencies to avoid a repeat failure or situation?
Great question. So I think Ryan and I both believe that at this airport, one consultant was in charge of the exploration program prior to designing the reinforced slope, design of the reinforced slope, QA/QC of the reinforced slope, and then subsequent monitoring of performance of the reinforced slope. So that to me is problematic. It would have been probably much better if multiple parties had been involved. And then, of course, a peer review for any significant structure like this was an independent peer review by an outside source would have probably caught many of the things that were obvious to this individual that asked this question.
Yeah, and of course, there are many publications that show the importance of peer review as the cost and complexity of a project goes up. The need and importance of peer review goes up as well. So, Jim and Ryan, thanks so much for doing this podcast. That's all the time we have today. If any of you have additional questions or would like additional information, please email me at fabricatedgeomembrane@gmail.com or visit the FGI website at fabricatedgeomembrane.com. In addition, Jim and Ryan's contact information are on the slide right after their webinar in the PDF that is on the FGI website. So Jim and Ryan, thanks again, and everyone, thanks for joining us. Bye.
Thank you.
Thank you.